Here is your DCP number 3 review. If you do not currently have a green formula chart with you, you probably need to get one. A lot of things that will be helpful on this review and for this test are going to be on this formula chart. The first part of this is the exponent rules. We're going to review our exponent rules. And I have a table here for us to fill out. We're going to write down the formulas with me, do one example problem, and you're going to do the rest of this table. For the product of powers property, for adding and subtracting polynomials, which is not on your formula chart, the formula would be a to the n plus a to the n equals 2a to the n. If the base and the power match, you add the coefficients. We combine like terms and we don't change the exponent. So for example, 3x squared plus 5x squared, 3x squared plus 5x squared is 8x squared. 3 plus 5 is 8. X squared does not change. We just change the coefficients. For the product of powers property, what this rule says on our formula chart, it's number 3, is that if you have a to the m power multiplied by a to the n power, same bases, all you do is take those exponents and add them together. This is the MA part of mad spam. Multiply, it means you add. So for the more complicated example here, we're going to line up the things that are alike. We're going to add together the exponents of letters that are alike. But if you have coefficients, big numbers, you're just going to do what it says to do, and it says to multiply them. 5 times 2 is 10. Then you have the x terms. X to the third times x squared. Well, 3 plus 2 is 5. It's x to the 5th power. Then I have the y's. Remember to line up only the letters that are the same. Y to the 5th times y to the 7th is y to the 12th power. I then have a z over here, and there's nothing that it combines with from the other part of this expression, so it doesn't change its exponent. There's nothing to add with it. The quotient of powers property is the ds part of mad spam, and it's number 4 on your formula chart. It says that a to the m power divided by a to the n power. When you're dividing, all you will do is subtract the exponents. The base does not change. So for the more complicated example here, we have, again, good old-fashioned numbers. Our constants, we're just literally going to do what it says, and it says to divide them. 30 divided by 6 is 5. And then when we get to our bases with exponents, we're going to subtract the exponents. X cubed divided by x squared is x to the 3 minus 2, which is x to the 1st power, or just x. And then we have our y's. Y to the 5th divided by y cubed is y squared. And since there's a z still chilling with nothing that it would need to subtract with or divide by, we're going to leave the z in our answer. The PM part of mad spam is the power of power property. For this rule, it says on our formula chart that a to the m power raised to the n power is equal to the a to the mn. Now, if you have parentheses raised to another power, that's the PM, power of power rule. And it's going to kind of look like distribution. It's not really distribution. You're multiplying the exponent on the outside of the parentheses to every exponent on the inside. So for the complicated example here, we make sure we know what the exponents currently are. The current exponent of 49 is 1. So when I start multiplying this to each one, half times 1 is a half. 1/2 times 4 is 2. Half of 8 is 4. Now I wouldn't stop here because I actually have a number raised to a power. This is something I can throw in my calculator or calculate in my brain. The 49 to the 1/2 power is really like the square root of 49. So this would be 7x squared y to the 4th when I finish actually simplifying this. So make sure you do not just divide 49 by half. This is multiplying times its exponent. Exponent to exponent multiplication, not big numbers. The third exponent rule, which is number 7 on your formula chart, is the negative exponent rule. The chart says this: a to the negative n power is equal to 1 over a to the positive n power. I like to call this the hammer time rule because MC hammer reminds me that I need to move and change. I move the base and exponent, I change the exponent to positive. Gotta make them happy. Okay, the example problem, you have 2r to the negative 3, s to the 5, t to the negative 6. You're only going to move the exponents that are negative. 2 has a current exponent of 1, which means it's not negative. The 2 does not move and change. So the 2 is going to remain in a numerator. The r has a negative exponent. So it is going to go down into my denominator to move and change. The whole r to the negative 3 moves. Move it to the bottom, no longer negative. S to the 5th power stays up at the top. It's positive, it's fine. But the t is sad and unhappy, it's negative. So we're going to move it and we're going to change it. 2s to the 5th power over r cubed t to the 6th power is the correct simplified version. You're no longer allowed to have negative exponents ever. Now don't just erase the negative, okay? Actually move and change it to make it positive. Don't just get rid of it. The zero exponent rule is so easy, it is not even on your formula chart. If you have any base raised to the 0 power, it's equal to 1, like a good old-fashioned 1. Now, only the term that is set to the power of 0 is 1. If you look at the second example, we have 5 times 0, x to the 0 power plus 4 to the 0 power. Well, this does not change to 1. This is the only part that changes to a 1. So this is really 5 times 1 plus 1. 5 times 1 is 5, plus 1 is 6. Last rule is called the rational exponent rule. We like to call this TIBO, top in, bottom out. TIBO rule says this, it's number 6 on your formula chart. If you have a base raised to a fraction exponent, you're going to rewrite this into radical form where the base does not change, the top number is inside, the bottom number is outside as an index on the radical sign. Not in front of it, on it, little. So if we look at the first two examples here with x's on them, we have x to the 3/4 power. I'm going to rewrite this in radical form, but I know that the base should not change. After that, I take the top number and write it inside. I take the bottom number and I write it outside. X to the 3/4 power is the same as the 4th root of x cubed. I can go the opposite way. Top in, bottom out. The base does not change, so if I have the 5th root of x to the 4th power, the base does not change, but the top number was inside, the bottom number was outside. Oops, wrong color. Bottom number is outside. Make sure it looks like an exponent, so it should still be floating and be little for it to be a rational exponent. There's a quick review of your exponent rules. Yes, they get a little complicated when we put them together, but as long as you know Math Spam, TIBO, and the MC Hammer rule, you should be fine. Go ahead and fill out the rest of this chart. Meet you on the inside. We're going to do number 1. It starts our exponential functions here. Okay, worrying about exponential functions means we're no longer doing linear equations, we're doing lines. They're called exponential functions because in the equation, the x is an exponent. For this one, it asks me to label the domain and range, the y-intercept and initial value, draw the asymptote, and identify the equation of the asymptote. Okay, first thing I do is I have to remember what domain and range is, but luckily, we've got Dr. XY and Dolor the robot on our green piece of paper to help me out. Domain is the x's, and range is the y's, which means I need to describe this graph from the left to the right. On the left, we have an arrow going on to infinity, negative infinity technically. And on the right, we have an arrow going up to positive infinity because it keeps going that way forever and ever and ever. Which means if we have double infinities, our domain is all real numbers, or the fun and funky R. Now for the range, if I look at this graph, I know for exponentials that there's a line it can't cross, and that's called the asymptote, which we will talk about later, which means this graph is going to always end about here. So for the range, which is y, I know it can't cross that 0, but if I look up at the top, it's going to go up to infinity. So I have x's from 0 to infinity. And the way we would write that is that y is greater than 0. The whole graph is above the asymptote, so it's greater. If it was down here, like number 2, it would be less than 0 because it's all underneath the asymptote. The y-intercept is a visual point on the graph, is right here, where it crosses the y-axis. That coordinate is 0, 1. which means that my initial value, or A, the A value in this graph is going to also be 1. There should be a 1 in my equation for the A. Now I drew in the asymptote. It's a horizontal line. That means it's a Hoy line. This tells me that Hoy lines start with y. So it's going to be y equals, and since it's at 0, y equals 0 is the asymptote for this graph. On number 3, it says to write an equation for the given exponential function. Okay, we're going to take this table, and anytime I see a table, I need to start thinking, okay, I see a table and I need an equation for it. I know Desmos can help. In fact, I gave you a hint on what you need to use. If you have a highlighter, go ahead and highlight this hint right here. This is not on our formula chart, which means this is something we have to memorize. It is the regular exponential equation, which is how we're going to write it. We just need A and B, but it's the annotated version with the 1s and the squiggly line. That's what we use in Desmos to write an equation from a table. So we're going to pop over to Desmos for a second, get rid of everything else I've done in here before, and add this table in. This table is, pardon me, looking at the wrong page. This table is 0, 1, 2, 3, and 0.025. That's 125. Come on, Miss Quigley. Oh my gosh, I can't type today. There we go. 0.2, 1.6, and 12.8. Now, I can't really see what's going on here because it's all sorts of zoomed out. So if I press the magnifying glass to zoom, ooh, there's my nice curve. Now, I use the annotated version of the exponential equation, y1 tilde or squiggly line, a parentheses b raised to the x1 power. Immediately after I type that in, Desmos is going to show me the a and the b value that I need to use in my equation. So our equation is going to be y equals 0.025 parentheses 8 raised to the x power. Again, this is y equals 0.025 parentheses 8 to the x power. I don't have to use the annotated ones in the squiggly line when I'm writing an equation. That's only for Desmos to know it's running the regression for us. You can also take a hint here. We said that our a value earlier is always at the beginning. It's also my y-intercept. So we know that this equation works because it has the same y-intercept. And these are going multiplying by 8 every time. Okay, we're going to write some equations. For number 5, it says the school population of 1,200 decreases by 6% each year. We need to identify the initial value and rate, determine if the situation represents growth or decay, and then write an equation for it. Gave you another hint here because now that we're using growth and decay, we need to use the detailed version of the growth and decay formula, which is y equals a times 1 plus or minus r to the t. So instead of b just being a number, we have details in there that tell us if it's going to grow or decay and by what rate. A school population of 1,200. 1,200 is my initial value. That's my a value. My rate as a percent is 6%. My rate as a decimal, remember moving the decimal place twice, is 0.06. And since this says the word decreases, I know that this is going to decay. So I'm going to be using a minus in my parentheses, 1 minus r to the t power. There's two options you can write for me for an equation. You can write y equals a 1 minus r to the t, right? Here's my a, here's my r as the decimal, and here's the fact that it's decaying. But you might not see answer choices like that. They might hide the details from you and actually do the subtraction there. 1 minus 0.06 is 0.94 to the t power. Either of these are options. Unsure how the test writers will write a question for you. They're both valid. They're both the same. 1 minus 0.06 is 0.94. So it doesn't matter how you write it, as long as it is the correct numbers, using the right a value, rate, and the decrease. I highlighted number 8 to do, but it is almost exactly like that number 5, so y'all have got this one. We're going to talk about number 9. Okay, it says to identify the y-intercept initial value, domain, and range, then identify if it represents growth or decay. Number 9 says this graph talks about the value of a car. If I want the y-intercept, I'm looking for where this graph crosses the y-axis. I would have had to guess at where this is because it's not at a pretty, cross endpoint. But if you remember, our a value is our y-intercept. This means that our y-intercept is 0,21,500 because that's the a value, and that's also where the graph crosses the y-axis. Our initial value is always the number part of our y-intercept. It's also the a value. And our domain and range, again, from our green sheet, we know, since Dr. XY tells me that the domain is x and the range is y. So domain, when we're looking from the left to the right, and range when we're looking from the bottom to the top. Domain for this one starts at 0. You can't time travel in Algebra 1, so this one's going to have a starting point right here, but it keeps going indefinitely. So we're going to say that the domain is bigger than 0. For the range, I'm going to look from the bottom to the top. Hopefully you remember that these sort of graphs have an asymptote here at 0. So 0 is my bottom. That's y. And if you look up at the top of this graph, it actually has a top. The car can't get more expensive than where it started. So our top is going to be 21,500. Since this graph goes down or decreases, this is going to represent decay because the curve decreases. Also, values of cars go down over time, so this is a decaying function. On number 12, we're going to talk about polynomials. The first polynomial we're going to do here is asking you to multiply. I know it's asking you to multiply because these two parentheses are smushed next to each other. So what we're going to do is we're going to set up a Punnett square. If you like to use FOIL, go right ahead. For the Punnett square, this is a binomial times a binomial. So I'd also set up a binomial times binomial Punnett square. 3x is in the top and -1. 4x and 9 go along the side. I start crossing these with multiplication, remembering all of my multiplication and exponent rules. 4x times 3x is 12x squared. 4x times -1 is -4x. 9 times 3x is 27x. 9 times -1 is -9. I've just done multiplication into each table, into each box. My like terms are here on my diagonal. And since there's a little cross in the middle of them, we remember that we're going to add these. 27x plus -4x is 23x. To write my final polynomial answer here, I'm going to take the top corner, 12x squared, all of my combined like terms, plus 23x, and my constant of -9, and create my polynomial answer. That's the product when we multiply 3x minus 1 times 4x plus 9. If I were to factor this polynomial answer, I should go back to the original linear factors that I started with. One thing I want you to remember about the FOIL or the Punnett square multiplication is that actually on your formula chart, number 21 has a setup for you. Now, if you're not multiplying a binomial times a binomial, your box will be bigger. If you're multiplying a binomial times a trinomial, you're going to have 2 and then 3. So it'll be more of a rectangle than a square, but the process is still the same. The next one we're going to do is number 15. Number 15, if you notice in the center, has a plus sign. That tells me that I'm going to add these polynomials. The only thing you have to do when you're adding a polynomial is CLT. CLT stands for combined like terms. So I'm going to line up all my like terms on the top and the bottom. Top parentheses stays the same, but the second parentheses, I'm going to make my bottom. I line up its like terms, making sure that they're actually like terms. 4x and 17x are like in the constants of 5. To CLT, I literally just add. X squared plus nothing is x squared. 4x plus 17x, that's 21x. And -5 plus -5 is -10. Make sure you're always adding when you CLT. You might be adding negative numbers, but always adding them. On number 17, however, this is not a combined like terms question because we are subtracting. The way I taught my students is to line up the opposites, since you're distributing that -1, and then you'll CLT or add like normal. Add the opposite. Subtracting is adding the opposite. So we line up the opposite like terms. So instead of 17x and -5, I'm going to line up -17x and a +5. Those are both the opposites of the second parentheses. It was 17x, now it's negative. It was -5, now it's positive. We still CLT, which means we're going to combine our like terms. X squared plus nothing is x squared. 4x plus -17x, that's -13x. And 5 plus -5, that cancels out, becomes 0. So our simplified, or our difference, is x squared minus 13x. Subtracting is adding the opposite. Adding is adding like terms. On this page, it asks us to factor. Now remember, the way that we learned how to factor is to use an X puzzle, but you should have your stop signs ready to always ask, is there a GCF first? Always ask if there's a GCF. Once you've answered that, if it's not a difference of two squares question, you're going to use number 26 on your formula chart to set up an X puzzle, and perhaps number 31 on your formula chart to solve the X puzzle so that you can get the factors. Remember, this is called swing and divide, so you should be dividing and potentially swinging numbers. If we look at number 18, 18 is a binomial, so I should already be thinking, this might be a difference of two squares. But my first question I asked myself, is there a GCF? And yes, there is. 2 and 72 are both divisible by 2, so I'm going to go ahead and take out my GCF of 2. That means 2 is in the front, and inside the parentheses, I'm going to have x squared minus 36 left. Again, I should be thinking, this is a difference, because I'm subtracting, of 2 perfect squares. If you don't see the difference of 2 squares, you totally can set up an X puzzle and solve, and factor it. But if you notice that this is actually, if I rewrite this, x squared minus 6 squared. The difference of two squares pattern is number 2 on your formula chart. And it says if you have something squared minus another thing squared, it factors to the first minus second, first plus second. So ours would factor out to x minus 6, x plus 6, with my GCF of 2 still chilling in the front. And that's the factored version of 2x squared minus 72. Remember, when you see there's two binomials, your spidey senses should be tingling, because maybe it's a difference of two squares and we can cut out some work. Again, if you don't see it, and right here you want to set up an X puzzle and solve it, totally fine. You'll end up with the same answer. All right, we're going to do number 20. The very first thing we do on any factoring question is we stop and we ask if there's a GCF. There is not a GCF between 1, 16x, and 64. So for GCF, we'd say no. So we just start with our X puzzle. A times C goes in the top, thanks to number 26 on your formula chart. That's 64 in the top and 16 in the bottom, and 1's underneath. Now, I'm looking for the factors of 64 that add to 16. Here are all the factors of 64. Now, if the top number is positive and the bottom number is positive, then my signs of my X puzzle should both be positive. It's what the magic number sheet tells me. The only way with two positives to make 16 out of this list is 8 and 8. So I would take both of these numbers and write it in my linear factors. We'd have x and a positive 8, x and a positive 8. Now, this is the correct answer, but you may see it in a reduced or simplified way. You may also see this answer as x plus 8 squared, because how many times does x plus 8 show up that I'm multiplying? There's 2 of those parentheses that are exactly the same. If there's 2 of the parentheses that are exactly the same, I can simplify it and say x plus 8 squared, because it happens twice. The next one we're going to do is number 23. The very first thing we do when we're factoring is we stop We ask, is there a GCF? Between 3, 11, and 6, there is no GCF. So I'm just going to go ahead and say no to the GCF question. And I can go ahead and start solving. Setting up an X puzzle and factoring. Sorry, I used the wrong verbiage. In the top is A times C. So 3 times 6 is 18. In the bottom is 11. Underneath the fraction bar should be 3. We're looking for factors of 18 that add to 11. And here are the factors of 18. The only one of these factors that, if I can add together and get 11, are positive 2 and positive 9. The first side does not reduce, it's still just 2/3, but the second side reduces to 3. So I would have the polynomials x plus 2/3, x plus 3, but that will not be an answer choice because this is called swing and divide. We've done the divide part. And if there's a denominator in our linear factors, we have to swing it forward. The correct linear factors for this are 3x plus 2 and x plus 3. That's factored form. Last one we're going to do together is number 24. We stop and we look at it and we ask ourselves, is there a GCF? Between 4, 16, and 20, yes. They're all divisible by 4. So I'm going to say that my GCF is 4, and I'm going to remember not to forget that part of my answer. And I'm going to divide each of these by 4. That would give me the leftover and smaller numbered equation of x squared plus 4x minus 5. From this new green one is where I set up my X puzzle. A times C in the top, B in the bottom, and A's underneath. The numbers that multiply to -5 and add to 4. Oh, 5 is prime, so that's it. That's the only one on this list, is 1 times 5. If the top number is negative and the bottom number is positive, then that means that my signs are going to be different, but the bigger one is going to be positive. So I'm going to have a bigger positive number and a smaller negative number, which means the 5 has to be bigger and the 1 is smaller. These factors, once I do my division, would be x plus 5, x minus 1. And I really hope you're saying, Ms. Quigley, you forgot something. Because if I let that GCF disappear and not include it in my final answer, that is not correct. If you take out a GCF, the GCF has to be in the very front of your factored form. It is one of my factors. It's a scalar factor, but it's a factor nonetheless. This is not a problem on your notes or on your review here, but hopefully you noticed that 26 is the same question as the one right above it, which is number 23. So I'm going to talk to you about a little something different before we go. So this is the same problem. Oops. Let's say that instead of that, I'm going to have the polynomial 2x squared plus 8x plus 3. Okay, that's the polynomial I'm given. We stop and we say, do 2, 8, and 3 have a GCF? No, they don't have a GCF. So I go ahead and set up my X puzzle. A times C goes in the top, B goes in the bottom, and A's go underneath. If I make a list for 6, only 6, because we're only making a list at the top, it's 1 times 6 and 2 times 4. And hopefully you're like me and you're looking at this list and saying, well, if the top is positive and the bottom is positive, then they're both positive. So there's plus and a plus, but 1 plus 6 is not 8, and 2 plus 4 is not 8. So there's no more combinations. When this happens, when you can't actually solve your X puzzle, this polynomial has no real factors. We would call it not factorable. Or you might see the phrase no real factors. In Algebra 2, you will learn how to factor a polynomial like this, but we don't do these in Algebra 1. If we can't factor it, we can't find numbers that multiply to the top and add to the bottom, 1, check your work and make sure it's not actually there and you missed it. But 2, if legitimately it's not there, this polynomial may be not factorable and may not have real factors. Hopefully this review helped you. You have problems now to practice on your own. You need to make sure you understand all of your exponent rules. You understand exponential functions and how to graph them using Desmos, and then use Desmos to write their equations from tables. And then how to do the 4 types of polynomial arithmetic: multiplying with the Punnett squares or FOIL, adding, subtracting, and factoring. Those are the things you're going to need to have a mastery of before we take this DCP. Y'all have a great day.